In this video, we'll be looking at polar coordinates. The first thing we want to do to fully understand polar coordinates is look at the graph of a polar coordinate. I've drawn a horizontal line here. It's extending from only a single point. That single point is called the pole. This line extending to the right is what we call the polar axis. That polar axis extends infinitely, and we count along that polar axis much in the same way we might count along the x-axis. So for instance, this would be 1 unit. We have 2 units. And we can define these to be as big or as small as we want to, as long as we're keeping those consistent distances. The difference between the polar coordinate system and the rectangular coordinate system is that I don't care about how far left and right I'm moving or how far up and down. What I care about now is the angle between my polar axis and what I call my terminal side. We've discussed the terminal side before. So now I care about, one, the angle that it takes to get to this terminal side, but I also care about where I am along that terminal side. So maybe I'm at a point, say, right about here. What we care about is the angle and the distance. That distance would be the distance from this pole to that point, that distance in green. So when we're defining a polar point, a coordinate in this polar format, and those points always take the form r comma theta. R is the distance from the pole to our point, and then the theta gives us the angle between. Let's take an example of this. So let's say we have the point 2 comma 45 degrees, and I want to plot this. So I'm going to draw out my polar axis. I'm going to start with my pole, and my polar axis extends off to the right from there. So I want to be 2 units away from the pole, and I want to be at an angle of 45 degrees. Now we know a 45-degree angle would put us somewhere up in here, right? The 45-degree line looks something like that. That would be 45. But I need to know where that point is actually going to sit on that line, because the terminal side extends infinitely, but this point should be only a single point. So to do that, I know I can count along this axis the same way we did up here. I can count out over 1 and then 2 units, but then the problem is I don't know where that sits along the R. The horizontal distance is very easy to measure. This diagonal is much more challenging. So what I'm going to do is I'm going to extend circles around the pole. There's my circle for a distance of 1, so I know right now where this thing would be hitting right there. Use my arrow to indicate. Right here, that would be at a distance of 1. But I need a second circle. I need that distance of 2. And so now I can see that circle's passing through a unit of 2. I know everywhere on that circle will be a distance of 2. And so my point, I'm going to put in blue, will be right here. That will be my polar coordinate. So a lot of times what we'll do is we'll just start with that set of circles on my graph. So I'm going to go ahead and draw this real quick. And so now I've drawn my polar axis. I've drawn those equal circles around the pole. The pole should be in the dead center. My drawing's not perfect. And so each of these circles is representing a set number of units that are all equidistant from the pole. I can let those circles represent whatever I want. So let's say this time we have a point that's a little bit larger. Let's say we have the point 5. Let's do 6 comma, we'll do 210 degrees. Well, I don't really want to have to draw 6 circles, so what I'm going to do is I'm going to just change the scale. I'm going to let each of these circles represent, say, 2. Could have used 3 as well, but it doesn't matter. So this would be 4, and then this would be 6. So if I'm going a distance of 6, that tells me I'm going to be on that third circle. I want to find an angle of 210 degrees. Well, this is 180. We'd get 30 degrees past it. And our point would be right about there. And again, this is a little bit of an approximate without using a protractor. But that would be my point. Up in my first example, I actually drew that terminal side to show the angle, but here I'm emphasizing my point is only a single point on the circle. It is not the actual line, it is just that single point. We can take angles that are larger than 360 degrees. We know how to find the coterminal angle. The coterminal angle, we'd take our 400. We would subtract off the 360, and we would get a remaining angle of 40 degrees. So this one, again, is a unit of 6. So if I use my circles of 2 apiece, and I'm only going to label the first circle this time, I know that would put me on the third circle out, an angle of 40 degrees, so just under the halfway point would be approximately right there. Let's look at an angle that's a negative. So this time I have the point 2, negative 100 degrees. So I know I'm going to be on the second circle, and we know that negative angles always make us travel backwards. So I'm going to go a negative 90, just a little bit further. Negative 100 would put me just past. Now obviously there's another way I could have gone to this. I didn't have to take that negative path. I could have used a coterminal angle. So I could have said, well, 100, negative 100, is the same as if I had added 360 to that. That would be the same as 260. Notice if we took a positive route, we would have got to that 260. But one thing that's a little bit different with our polar coordinates is we can not only take negative angles, we can also take negative lengths of sides. So let me reset this problem with a negative length. Now I have a point negative 2, 50 degrees. We know we're going to be on the second circle because that is our length. We want to take an angle of 50, so that would put us just over the halfway point. And so I would expect it to be right about here if it was a positive 2, but it's not. So we have to think what we're doing is we're going in the opposite direction. Negative, this is a length still, but it's a negative length, which is sending us the opposite direction. So if we think about the first side going this direction, we're going to go the exact opposite way. We're going to end up on the exact wrong side of the circle of what we would have initially expected. Our point will be right down here. And so we can always get to a point not only through changing the angle, but also through changing the side. We can use positive and negative sides. What this does is it gives us multiple ways to write out our polar points, or multiple representations. So anytime we start with an angle, we'll call it r comma theta. Well, we can write that r comma theta in multiple ways. For one, we saw we can take that r and leave it the same, and we can change the angle using our coterminal angles. So we can add or subtract 360 degrees, and we'll always get back to the same point, and that's not a problem. But we can also change our r. We can make the r negative, but what that means is what we saw in this example right here is we end up on that wrong side of the circle. So what that means is we could have taken the angle, we could have added 180 degrees to it, we would have ended up at the exact same position. We could not only add, but we could also subtract 180 degrees. And we'll take a look at that previous example to see how that works. We start with the point negative 2, 50. We could have taken that and changed the angle. We could have added 360 to that. I want to subtract 360, it doesn't make a difference, so I could have had negative 310 degrees. So if we think about that, we would have gone round backwards to the negative 360, and the negative 310 shorter than the negative 360. We would have traveled backwards, obviously giving us the same angle. We also could have changed the r value to a positive 2 and then added 180 to my angle. If I add 180 to 50, that would be 230 degrees. And 230 degrees, we'd go 180, we'd go 50 further. It's going to put us at that exact same position. So we have multiple ways we can write out one point. Obviously, if we're looking at these points on a graph, we can look at them in terms of not only polar coordinates, but also in terms of rectangular coordinates. I can stick my xy axis back on top of this, and I could redefine these in terms of an x and a y. We see that clearly this point right here has an x coordinate, we don't know exactly what it is, and it also has a y coordinate. We think about how we might find that position. Well, what we see is that we have a right triangle. So if I want to find the x position, that would be my adjacent side, and the trig function that allows me to find the adjacent side is the cosine. If I want to find the opposite side, the y over here, that would be using sine. So to convert from polar to rectangular coordinates, to find our x is going to be equal to the r value times the cosine of r theta. If we think about where that equation is coming from, we already said that the x is the adjacent side, so the x is going to be involved with cosine. Cosine theta would be equal to x over r. Multiplying the r over, we get r cosine theta. To get our y, well, we're going to use the sine. Y is equal to r sine theta. Again, the r coming over because initially we would have sine theta is equal to y over r. We're solving. So let's take this point negative 250 and let's convert to rectangular form. So my x is going to be equal to, my r is negative 2 cosine, and my angle was negative 50, and that is a degree measure. I'm going to use my calculator, and when I do, I get the answer of negative 1.29. I'm going to do the same thing to get my y, but I'm going to use my sine, so negative 2 sine of the negative 50. And when I do, I get negative 1.53. If we were to look at this, it looks like my x-coordinate just over the 1. We can see that because our circle represents 1. And we would see a y value that's not quite to that bottom of that circle there. So my graph not perfectly drawn, but we can see that that is approximately the negative 1.53. At the very least, we see it's in the correct quadrant. That is something to note. It's a good idea to always draw these things out to think about which quadrants they're in. It's a good way to make sure that we don't make a simple mistake, and it's just a good way to make sure we have it placed in the correct quadrant. That's especially true when we go to convert the opposite direction. To convert from rectangular to polar coordinates, well, let's start with the example on this one and then we'll define our formulas. So let's say we have the example, the point 2, negative 2. So the first thing I'm going to do is I'm going to sketch that out. We know that 2, negative 2 would be in the fourth quadrant. 2, negative 2 will be somewhere right around here. And so if I know the x and the y, and I want to get the r and the angle, well, obviously we're going to use our right triangle trig again. So to find my angle, or let's start with the r. To find the r, we can think about the Pythagorean theorem. R squared is going to be equal to x squared plus y squared. Our r squared will be equal to, the x was 2 squared, which is 4. The y was negative 2 squared, which is 4. Of course, that gives us 8, meaning that r is going to be equal to the square root of 8, which we can simplify to be 2 square roots of 2. So now that we have the r, let's find the theta. Well, to think about how we're going to find the theta, we have the opposite, we have the adjacent. Well, tangent uses those parameters. We're looking for our theta, and we know that's equal to the opposite over the adjacent, that y over the x. which in this case, that tangent theta will be equal to the negative 2 over 2, which is equal to negative 1. Now, when does that occur? Well, we know that one. We don't have to use a calculator for that one. We know tangent is equal to negative 1 at an angle of negative 45 degrees. We could have also used the positive. Anytime we're talking about the inverse tangent, we do want to define it in that fourth or first quadrant, but we don't really need to use the inverse tangent here. We're just thinking about when something is true. And so because it is in the fourth quadrant, we could use the negative 45 degrees. I could also use the positive version, the 315 degrees. But that does bring up a good point, that if I had had the point negative 2 comma 2, we'd set up everything the same way. We'll get the exact same r value. That won't change. We would say that, hey, when I take the inverse tangent, I would get negative 45, but the thing to keep in mind is that negative 2, 2 is actually in the second quadrant. So we can't use necessarily what the calculator gives us. We need to think about where these things are placed, and that's why I recommend drawing a picture first. If we think about negative 2, 2, it is in that second quadrant, and so, yes, when I take the inverse tangent of the negative 1, the calculator would tell me the answer is negative 45 degrees. I've got to be the one that's smart enough to recognize, well, no, that can't be right. That's not what I should be using. My theta is, in fact, going to be in the second quadrant. So I need to take that, I need to add it to 180 degrees, or just use your reference angles, subtract the 45 from the 180, and get the 135 degrees. So whenever you're converting from polar to rectangular or from rectangular to polar, it is always a good idea to start with that sketch first. That will eliminate a lot of simple mistakes. But I did say we'd define those formulas, so let's go back and formally do that. If we want to convert from rectangular to polar, if we want to find the r value, we are going to do that by using the Pythagorean theorem. So our r will be equal to the square root of the x squared plus the y squared. And if we want to figure out what the theta is, well, theta will be equal to the inverse tangent of y over x. But I'm going to kind of put a couple of stars there, a couple asterisks, because we have to pay attention to which quadrant that is in. And so for that reason, it is always a good idea to draw the picture. Now, there is one last thing to keep in mind, which is if I had not wanted to use the 135, if I had wanted to use the initial 45 that the calculator had given me, I could do that. I would have to use a different r value. Up here, we found the r value to be the 2 square root of 2, and that was correct. But if I want to use a negative angle, then I'd come back here and I'd make that r value negative, because I have the ability to use multiple representations, multiple ways to write out these points. If I were to go negative 45 and then backtrack along that line, 2 units, I'm going to end up in the second quadrant. So this is yet another way to draw the correct, to get to the correct point using these two r and theta values rather than the initial one that we had found. Always important to pay attention to the quadrant so you can adjust the angle or adjust the r value. In the examples I just completed, I used degrees. You can also use radians for any of these problems.